Uh, Welcome, everyone. It's my pleasure to introduce our speaker today, Professor Shailesh from Duke University. So Shailesh got his PhD from Columbia, and then he was a postdoc for a couple of years at MIT before joining Duke, and he's been there for several years now. He's received many awards, including the Fellowship of the American Chemical Society and the DOE Outstanding Investigator Award. So Shailesh does a lot of work on using numerical simulations to study many body problems, which are of interest both for condensed matter and for high energy and particle physics. And so today, he will give us some overview of the things that they've been doing recently, trying to develop new tools to try and understand some of these questions coming from particle physics. So please join me in welcoming Shailesh.
So thank you, Arun, for inviting me. I've usually passed Toronto on my way to other places like the Perimeter Institute, but never come to the university here. But so thank you for inviting me. So the talk I'm going to talk a bit about is some of our recent attempts to understand if we can build the universe out of qubits. Now, let me say a disclaimer at the beginning. This is not going to be this new exciting field of research on using quantum computers in physics, right? I'm not going to talk anything about how to put my interesting questions on a quantum computer, but the fact that you can perhaps do it sometime in the future is the exciting part for me, and I'm using that motivation to sort of explore if some of the things that we have been learning about in terms of the universe through our experiments can actually be someday be formulated such that it can be put on a quantum computer. So that is that disclaimer out. Let me tell you a bit about my collaborators. Hirsch and Hanqing were my students. They passed. Both of them are postdocs at the moment. My long-term collaborator, who was one of the inspirations to do this long ago, actually, we started doing some of the things that I'm going to tell you even as a postdoc at MIT. He's at Bern. And then these two are my lattice colleagues who have gotten excited about some of these new ideas recently. So the talk I have sort of focused on 4 questions, right? It's going to be a very low level. Please feel free to ask me questions as I go along. Hopefully, I have not many slides that I can finish in time, but we'll see how things go. If I feel like I can answer it at the end, I might tell you to wait. So the 4 questions that I will try to think about are, I'll begin with just some reminder of what we think the universe is made out of today, right? Then I will, that will naturally lead me to something very interesting that often is missed when we talk about sort of how the universe is made out of, is that at the deep, at some depth, one has to understand that we have to think about the universe is made out of quantum degrees of freedom almost at every point in space. So that's why we'll have to talk a bit about quantum fields. It's a really difficult topic. Even after 2 or 3 graduate courses, you still sort of struggle to understand what that means. So I have this challenge to explain it to you, what all that means. So we'll try that. I'll try that. Because that is going to be my motivation to then tell me why I'm interested in, or even how I'm going to try to do that using a quantum computer. And that is my motivation of trying to put this in, construct that quantum field using qubits, right? And then I will show you some results, which is again going to be watered down quite a bit. But I hope that even experts after, I'm sure what I'm going to say in the first 3 will be, you can go to sleep if you are an expert in quantum field theory, but then maybe you may want to wake up there because we find something very exciting and interesting, which then makes us feel that maybe we are on the right path, right? That's how sometimes physics goes. and then I will summarize. So let's begin with the first question. What is our universe made of? And often when I think about this question, there is one fundamental debate, which I'm sure happened many millennia ago, between Democritus and Aristotle, right? I'm sure they also were thinking about what is our universe made out of. And if you think about it, when we look at the real world, we can see two types of objects. One is sort of discrete in some sense, right? Maybe the sand that these people are standing on. And the other looks like a continuum, like the water. And so at that time, of course, we didn't have a deep knowledge of things. And so the question was, is the universe made out of discrete objects at its fundamental level? Or is it some kind of a continuum, which then looks discrete? Maybe it breaks down into small parts in certain cases, but at the deep level, it's a continuum, right? Of course, at that time, if these two are debating, I think we should have taken the viewpoint of these two more intelligent creatures, that you just have to wait for some time before we can really answer this question. It's a very deep question to understand. You can debate about it forever, but you'll never get an answer, right? But if you will, if you let me go, we are exactly at that same level even now, but at a much more intricate thing. The same debate is going to continue, right? So this is going to be sort of the theme of the talk. So the main difference is that sometimes you might think about it as made out of discrete finite objects, or maybe there's something continuum and you have to deal with infinities at the end of the day. The modern perspective, of course, we all know, is that the atom that Democritus was all looking for is actually there, right? But then if you dig deeper, there is another particle which we call the nucleus. And if you get deeper there are other things that it consists of. And today, we think about even a proton is not a simple object. It's actually consisting of lots of interesting things going on inside the proton. We believe that it's made out of quarks, and quarks are glued together in terms of gluon, right? So that's sort of the thing that we've learned in so many centuries. So right now, we believe that there is a model that we call the standard model of particle physics, which has classified all the particles that we have seen so far, right? So we classify them in terms of two classes of particles. One is we call fermions, and we'll see what the difference between these two are as we go on. And then there are a bunch of bosons. And these particles apparently interact with each other to create the universe that we know of, right? I'm not going to get into the details of all the interactions because that is a much more interesting and a difficult question. But at our level, let's stick to that. So in that sense, you might say, well, finally, at least as far as we know today, maybe Democritus won the argument, right? It's all made out of discrete objects interacting with each other, and that's our universe made out of. But then if you think a bit more, these particles are not simple classical particles. They're all quantum mechanical in nature. And all of these famous physicists have sort of told us how to think about particles. So in fact, we know that particles behave like waves, right? And then those waves move in a continuum. And so that continuum space-time is what perhaps is more sort of fundamental, right? In fact, if you take that a step further, indeed, if you think about the standard model and understand the standard model, the particles actually arise as excitations over some sort of imaginary, fictitious field, which is all quantum mechanical, right? That's the way we understand the model, the standard model right now. So the particles are actually living in a continuum. And so maybe actually Aristotle was right. Everything was a continuum. And the particles that we see are just excitations over that. But there is more to the story. We have to think about it and try to understand what's going on. So now we get into this whole notion of why do we even need this notion of a field quantum mechanical field before we can start thinking about particles. So for that, we need to understand a bit about both quantum mechanics, which I hope some of you learn about in your sort of undergraduate classes and maybe graduate classes. So one of the things about quantum mechanics is that when you take a physical system, you don't just look at the physical system as how Newton looked at it. You have to sort of think about it more abstractly as it's a state in some vector space. This is something that we teach our students and try to make them understand the intricacies of quantum mechanics. So quantum mechanics has two sort of complicated concepts of what we call a vector space. So the systems are all vectors. And then when you observe things like position of a particle, those are operators that act on this vector space. And those operators are like matrices that change with time. And so if you want to understand the properties of that observable, which is like the position, I have to then understand this operator at various times. And in that vector space, I will learn what the physics is. And so when you measure something, you get what we call the eigenvalues of this operator. And this is what we learn. But then in this case, the time is a parameter. On the other hand, the position is an operator. Position is an observable. And so you go back home, you feel, yeah, I've learned something about quantum mechanics. But then you also take another course in special relativity, which says that, well, actually, space and time are very similar to each other. They are not very different. Different observers actually see different space and time because they get mixed into each other. So we learn about symmetries that Einstein discovered. But then nature has both of them together. So we have to think about how to marry these two. And that's what this plus sign means. But then that was also discovered long ago. But there you need to think about quantum mechanics at every spatial point which evolves in time. So suddenly what happens is the concept of quantum mechanics still lives. You live in a vector space. But then the operators are no longer position, because position then becomes very similar to a time, right? And so you have to think about some other quantum mechanical degrees of freedom, which we call a field, a quantum field, that lives at every spatial point. And that is important before we can sort of marry these two concepts together. So in our nature, to really think about where we know that special relativity and quantum mechanics exist together, we have to start thinking about quantum fields. Okay, so that means let's just go back and sort of spend a minute on that. That means at every spatial point R and T, right, in a space-time point, there is a quantum mechanical object. Maybe there are two different objects. This acts like position that we thought about as position, but it's no longer position. It's some fictitious field. Then there's something like momentum, but it's not momentum. It's again a fictitious field. And these two are operators which have an interesting relation between them. And this is what we call a commutation relation, exactly like X and P don't commute with each other. But this is happening at every spatial point, right? At two different spatial points, they commute, but at the same point, they don't, right? And in this case, there's even a complication in terms of some infinity, and we'll come back to that in a minute, right? So that suggests that if you really think about it, there's some fictitious quantum mechanical particles, if you wish, that live at every spatial point, right? We have sort of position, but not the position that we talk about. It's some other space, and that is the field space. And that's happening at every point. And so that leads to the fact that since the space-time is continuous, remember Aristotle's point of view that everything is happening in a continuum. That means at every point, there is this quantum mechanical degree of freedom. And if you actually start doing calculations, you get into all kinds of infinities. The mathematics just doesn't work out nicely, right? So it suggests that something crazy is going on, right? So although we thought Aristotle won the argument, everything is continuous, something, maybe we are missing something. So let's try to think about it a bit more. So continue this debate between continuum and discrete. perhaps space-time is not really continuous. Maybe there is something at the Planck scale that's something that we have to really think about, because otherwise the quantum fields that we have written down and maybe the standard model we have built is not quite the right way to think about the problem, right? So maybe the space-time itself is some set of discrete points, right? It looks continuum because we have not yet probed distances at that scale, the possibility. And then there are operators that live on all of those discrete set of points. In fact, this viewpoint is what is being taken today in many of the research that's going on in terms of quantum gravity. By the way, I'm not an expert on this in this field, so we're not going to talk about this. But on the other hand, you can go back and read. There's lots of interesting, simple popular science literature on this, which then lead to all this other work that's being done. So I urge you to go and look at these two. So here is sort of a cartoon of how discrete quantum degrees of freedom finally leads to something emergent and something continuum emerges on the surface of this interesting quantum object. There's another field which has been there for quite some time now, where there's a belief that at the Planck scale, things are sort of not continuous, but made out of discrete objects. But that's not the point that I'm trying to get to, because that's not the field that I work in. You go back in the 1970s, this whole issue of infinities was being debated, and people didn't know how to think about how to deal with these infinities. A very deep insight came through Wilson. Right? He got a Nobel Prize for explaining to us how to really think about quantum field theory. So forget about quantum gravity or even gravity. Just think about simple quantum field theory, which you think about the standard model of particle physics today. So what Wilson proposed was that we should assume that space-time is actually a lattice, right? So at least to do the calculations, let's assume that, right? So then there are quantum degrees of freedom living on the lattice. And now all the infinities are gone because you just have a lattice, right, at the end. And so he proposed that space-time is actually a lattice to begin with, at least. But then that lattice would break all kinds of symmetries, right? There won't be the symmetries that Einstein really proposed, because the lattice, there's no lattice in the real world when you think about Einstein's special relativity. So it would break the symmetries that we were all thinking about. But Wilson argued that perhaps these symmetries would emerge if you tune things carefully in your theory. We'll talk about the tuning in a minute, right? So it's like a mathematical thing where you write everything in terms of discrete objects, and then when you do a sum, right, you have to do a sum to an infinite thing, and then you get something that's very interesting, right? So he said you just have to tune things carefully into at a particular point, which we call a quantum critical point today, right? If you tune yourself to that critical point, all the symmetries would emerge. It's like a limiting process in a mathematical description. That made things much more tractable suddenly, right? So now you could really understand quantum field theories nicely, right? Everything was finite. All at the end you had to do was take some limits to define your theory. And sometimes when we do this, we call this quantum critical point as a continuum limit to define the theory. So Wilson's viewpoint was the following. At every spatial point, when we talk about a field, there is a Hilbert space or a vector space at that particular point. And that vector space is actually infinite dimensional if it was a bosonic theory. Remember, I talked about particles that were bosons and some particles were fermions in the standard model. If it's a bosonic particle that emerges from a quantum field where there are bosonic quantum degrees of freedom at every point in your lattice, and these live in an infinite dimensional space at every point. On the other hand, if it was a fermionic quantum field, at every point, it'll just be a two-dimensional Hilbert space. This is where the Pauli principle plays a role. So it would say that you cannot have more than one particle at a given site. Either the particle will not exist or it will exist. So in some sense, fermions were a much more nicer and a simpler thing locally. But they have other complications when you think about globally, right? So in some sense, this was sort of the local way of understanding without infinities of what's going on in a quantum field. We'll come back to this infinity because at the end, we'd like to write all these, build our theories using qubits. This is going to play a role, right? So whenever we have a bosonic field or a bosonic particle, locally, Wilson would say we start with an infinite dimensional Hilbert space at every point. And of course, all these interact with each other and create our theory for us. Now, what about a quantum particle? Suppose I want to do just quantum mechanics, right? I want to study a particle in a box, right? We know that the way we do this is we think about the particle's position as an operator, right? And it has certain values it can take, right? And then we write down wave functions of the particle and so on. But Wilson would say, well, think about it from the quantum field theory point of view. What it would say is if you had a particle in a box, the first step is to discretize the space here and write it, think about this as a lattice, right? So there are your lattice points and the particle that you're thinking about is sitting here and all the other sites, remember there was a Hilbert space at every site, is just an empty site. Remember in our description of a boson or a fermion, at every site, there is a possibility that the particle existed or not, right? And if it's boson, I can put, of course, pile up many particles on a single site, and then it'll be a superposition. Okay, that's quantum mechanics. So here, if I wanted to just do quantum mechanics of a single particle, I'll just put every other site to be empty, and I'll just put the particle there. Now, of course, the Hamiltonian will then evolve the particle, so it will just move around in this space. But then the lattice is sort of artificial. So I have to take, remember that tuning I have to do. So that is the second step, that I have to tune the self to a quantum critical point where I get back the physics of my continuum. So always when we think about quantum field theory, we have two steps. We first discretize the space, right? Make everything finite. Then think about quantum mechanics at each point. And then at the end of the day, whatever quantum mechanics we are thinking about, we write down the theory and then find a parameter so that we can take the lattice spacing to zero. That is what we call the continuum limit. Now, particles, of course, are more complicated in quantum field theory. Here is an example of quantum mechanics. In principle, when we think about a single particle, what can happen is, in addition to that particle, there can be more particles, that particle anti-particle pairs can get generated out of the vacuum. So in some sense, the single particle physics is not just of this, but this plus that plus that. Remember superposition, right? So all of these are in principle possible for a single particle. So even a single particle is actually an excitation in this complicated whole space. That's the whole thing about a quantum field, right? And that's the spirit in which we understand how particles emerge, right? So what Wilson taught us is this continuum that we were thinking about. It's at least better to think in terms of a lattice, right? Something discrete. We don't quite know if it is something fundamental or not, but at least it helps us understand the theory much nicer. Okay? So every single particle, as I mentioned, is actually a superposition of many excitations, right? Over the background. Now, what about the continuum limit? I've been telling you that you have to tune yourself to a continuum limit. What does that even mean? Right? What Wilson said is that there is actually a parameter in the theory that keeps all physics the same, except that changes the lattice spaces. How can that even be possible? In principle, it's very hard, but let me tell you show you a cartoon of how this might emerge. Right? So here is some kind of a understanding of what I'm talking about. So let's say I'm thinking of a proton, right? The proton is made out of 3 quarks. There's some size of the proton, right? Let's call that size C. That's the physical size of the proton. And notice there's a lattice. And so this C is 4 times 8. You see 1, 2, 3, 4. So I measure everything in lattice units, and the length of the or the size of the proton is some number of lattice units. And when I do a calculation, this is what I see. And all of this happens at some parameter in my theory. Let's call it G1. G is a parameter in my Hamiltonian that I kept as at some value G1, and I got this. Then what Wilson says is that I change that parameter to G2. The proton remains the same, but now notice the correlation length in lattice units has become 8 times 8. Right? The proton has the same size, but now it's being viewed from a lattice which is smaller. Right? I just had to change my parameter, and that's what then, if I do the calculation, is correct. Now, if I take it to another parameter, G3, now again, this remains the same, and now notice that in terms of the lattice spacing, it has become, the lattice spacing has become smaller. Right? Notice that the physical length diverges in lattice units. Right? It's becoming more and more in lattice units. And that's the way continuum limits emerge when you do a problem on the lattice. Right? And this was a revolutionary idea at that time in the 70s. And people have gone and taken this very seriously and done a lot of calculations. And today, there's a lot of calculations and theories which we cannot otherwise solve using this approach. So what Wilson showed us, if we just summarize, that quantum field theories emerge from lattice field theories. I mean, say, when I say quantum field theories, continuum quantum field theories is what I'm talking about. From lattice field theories, when physical lengths diverge in lattice units. Right? This actually occurs in condensed matter physics. Right? If you take a material and tune yourself, maybe tune a magnetic field or tune some other doping or something like that, right? You can go through what we call quantum phase transitions where correlation lengths diverge. And these are what are called second order phase transitions, right? So here is a sort of a cartoon of such a thing, right? That's temperature. At 0 temperature, I'm just tuning a coupling, right? There are 2 phases and it's going through a second order phase transition. And what Wilson was proposing was that close to that transition is where an interesting quantum field theory will emerge, right? And so QFTs naturally arise near quantum critical point. The question is, what quantum field theories arise is an interesting question of research. You start with this particular lattice model with these degrees of freedom. This is the Hamiltonian you start with, and then you tune yourself. At some quantum critical point, if you see a quantum critical point, some interesting quantum field theory will emerge. What is that? That's an interesting question. But if you are interested in a given quantum field theory, then you'll have to devise a method to figure out what is the lattice Hamiltonian to start with and how do I tune mine. Right? So all this, Wilson gave a very nice picture in terms of what we call a renormalization group approach. What he said was, well, there are all kinds of parameters in our model because the physics at the end depends on how the interaction strength is, what really are the fields in our theory, right? What exactly should we do? So these are all the space of all microscopic models that you can write down. Quantum field theories are very special points in this space. And they appear at some point which we call the fixed point. And then there are couplings where if you're slightly away from that fixed point, it'll go away. These are called relevant couplings, he said. These are the things that give you mass scales and masses of particles and all that. But then there are also other directions in our theory which are irrelevant. It doesn't matter what couplings you pick for those, right? At the end, the physics, what you're interested in is in the vicinity of this point. That's what a quantum field theory is all about. And then he said, well, you take a lattice model and you tune some parameter. You might cross this line somewhere. That is your quantum critical point. And then the physics at very long distances compared to that, you will remember we said there was a diverging length scale. And so at length scales much larger than the lattice, the physics will be that of the quantum critical, well, of the quantum field theory. You can do many things. You can take a different lattice model. So the microscopic lattice models are not important. You can choose many different models and get the same physics at the end of the day, right? And this is what we call universality. Now, well, we have understood so much about quantum field theories because of Wilson. Why don't we just take that Wilson's approach and do all kinds of calculations that we are interested in, right? And this is what people have been doing since the 1970s, especially in the sector of strong interactions which involve nuclear physics, right? If you think about how a proton is formed, I showed a cartoon how the three quarks were interacting with gluons. And there's a lot of interesting quantum mechanics going on, and it's very hard to do that on a piece of paper. So, but we can use maybe Wilson's approach, and that's a field what we call lattice QCD, right? But unfortunately, although this whole approach is in principle doable, the calculations can be very difficult, right? Because as you can imagine, there is a quantum degree of freedom at every lattice site. You have removed infinities, but now think about just putting a particle at every lattice site, maybe even a one-dimensional particle. They're all interacting with each other. There's a particle at every lattice site. Now, as the lattice sites become bigger, you have a many-body problem, right? All of these are interacting. It's called a many-body quantum mechanical problem. That's very hard, and it's not easy to solve, right? In fact, let me demonstrate this in a very simple example, which you all can take home with you. So if you think about a fundamental particle, right, like an electron, I'm going to imagine an even proton as a fundamental particle here. Now we know it is not, but I'm going to tell you what the difficulties are. So if you take a point like particle in quantum field theory, which Dirac explained long ago, and if it's charged, right, it actually has a small magnetic moment associated with it. And you can actually calculate that magnetic moment. There's a simple formula, and this G is a dimensionless number, right, which is supposed to be 2 if the particle was just freely floating in space, right? To understand this, you'll need to do what we call a Dirac equation. The physics of this is there in the Dirac equation. Dirac found this. But then if you add some interactions, remember I told you, typically the particle is not a single particle. Typically, there are also other excitations. There's a particle-antiparticle pair. And so that number 2 will get changed. So there is some extra factor that you need to add. And so that delta tells you how strongly that particle is interacting with everything else, right? And so people have measured this delta for the electron, right? So the experiment gives you this number. Notice how precisely it's known. And the theory also produces this number. And you can see that theory and experiment are extremely consistent with each other, right? And so this is, in fact, one of the triumphs of quantum field theory. And it's sort of something that we all feel proud about, that we really understand nature at that kind of precision, right? If I do this for muon, again, I get very good agreement. But now if you look closely, there is beginning to see some discrepancy. And this is, this discrepancy is now described in this paper. And now it's causing all kinds of excitement in the physics community. Imagine where we are kind of thinking about where the excitement is, right? It's not about the first few decimals, it's at that point, right? And this is like, wow, we have found some new physics, right? And so we'd like to understand that better. Notice what happens for a proton, right? So the experiment is very precise, but the theory is terrible, right? This is something that Wilson thought he would solve when he proposed this approach in 1970s, and today we are still struggling to figure out what is going on. How do we calculate this? So what I want to bring out is the computational bottleneck. Right? Although we know how to do the calculations in principle, to do this calculation is very hard. It's fundamental physics. Remember, it's the physics of a proton. And I just want to know what its magnetic moment is. I know the theory, but I don't know how to do the calculation. Right? Now, if you think about the graph as to what that produced, here is the graph in this paper. It's a few years old now. My colleagues will tell me, no, you shouldn't take this picture. You should give me, my calculation is better, but it'll be maybe better by a factor of maybe 0.8 better. That's it. Like that error bar is maybe shrunk like that. Not a whole lot better, right? But on the other hand, notice there is no precision here, right? That does not mean, I must point out, that does not mean that there are not other quantities that we have calculated which are very precise, right? Not maybe as precise as that other calculations, but they are much precise than this. And this is like a bad quantity. And my colleagues will tell me, no, you're projecting the wrong side of our community. We have really done a lot of interesting work. That's actually true. There's a lot of work that has been done, but my motivation is that maybe we should look for something better, right? What about other quantities? For example, I'm interested in understanding how nuclei form, right? The simplest nuclei binding is between a proton and a neutron, right? That's a deuteron. And so we can say, well, can I calculate the binding energy of this particular object? The binding energy is being measured very accurately, and that's our result at the moment, right? Again, this is some years old now, but we are really far, far away from any precision. So if there is some interesting new physics hidden in this, like how we were excited about that muon, we just can't go to that at the moment. Now, the difficulties in these things is from our understanding of how to do the calculation, right? Wilson taught us how to do the calculation, but remember, we are searching for a vector in this multi-dimensional Hilbert space, that there is an infinite dimensional Hilbert space at each point, the quantum mechanical space, right? And we want to know what is a proton. Proton is a vector in some direction. I don't know how do you decide where the vector is? You need a basis, right? And then from that basis, I'll tell you where that vector is. This component is this much, this component is this much, right? And so I want to know where this vector points. And so I choose a convenient basis, but that vector space is huge, right? So there are sort of an exponentially large number of components for this vector. And so I need to know where all those components are, and that convenient basis is the wrong basis. I need maybe some other basis, and nobody knows what that other right basis is at the moment, right? So it's like searching for a needle, right, in a haystack. You have lots of possibilities, you just have to figure out which one it is. And we have techniques which we call Monte Carlo, which seems to work in some cases, but it's usually very hard. Now, if you want to think about real-time processes, right? So there are lots of real-time processes. For example, I'd like to understand how nuclear fission occurs, right? How nuclear fusion occurs. Maybe there's a whole big experimental program where I take two big nuclei and smash into each other, right? You can imagine easily that once I put in quantum mechanics, it's going to be very hard to do this evolution in time. I know how to do it, right? It's all unitary time evolution, but in a very, very high dimensional Hilbert space. So clearly there is some room for thinking about it out of the box. What exactly should I do the calculation in? Is there anything else we can do? And this is where the recent excitement in quantum computers come in, right? Can quantum computers help, right? Of course, this is again not a new question. Feynman asked it long, long ago, right? In fact, there's a nice paper, if you have a chance to read it. He was sort of exploring how to think about nature, right? How to think about maybe computing things in nature. But then, since then, John Preskill is been proposing that maybe someday we will have this, and gotten very excited about this field of quantum computing. Instead of hyping, you can just ask if at all this is possible, right? We don't know when it will be possible because it requires technological breakthroughs in many ways. How do we simulate a quantum field theory in a quantum computer? That is sort of the goal of my reason to build our universe out of qubits. Right? But it's not clear that this is going to help because we are just learning about how to formulate the problem. But in principle, it's sort of obvious that maybe there's something that might emerge, right? That's very clear. So because instead of classical bits, remember in this big vector space, I had to figure out where that vector was sitting. In classical computation, I needed to choose a basis, and then I had to figure out what the components are, right? And remember the basis was very high dimensional, right? Here, if you take a simple qubit, it's two-dimensional to begin with, right? And now if I have 100 qubits, I'm already exploring a 2 to the 100 dimensional Hilbert space, right? All of these qubits could maybe form together in some coherent way, and now I have a vector in this 2 to the power 100 dimensional Hilbert space, right? So I can at least build very high dimensional Hilbert spaces using a logarithmic number of qubits, right? Now, quantum computers can in principle store the end when everything works out, maybe an entangled system of these qubits, and so maybe it will be pointing in the right direction of a proton, for example, right? And it can even evolve it in time. So maybe if it can do one proton, maybe it can do two protons, and maybe it can do a deuteron, maybe it can do small nuclei, right? So this is sort of the hype, right? We don't know whether it's going to happen, but at least it's a fascinating question. How do we go about even writing down a theory that involves quantum fields to be able to solvable on a quantum computer? So here is a quick circuit model. So here's a simple circuit model. Not going to get into it again. So in principle, we can design quantum circuits where you can start with some unentangled state, evolve it using some adiabatic evolution, so that the ground state of this theory slowly evolves, and the Hamiltonian has a ground state to some very interesting state, some entangled state. And so people are exploring these ideas, right? So this is the amount of quantum computing I'm going to talk about in this talk. But then there are questions about what is the noise, what do we measure, how do we do things, and this is like a very interesting, exploding field of research, actually. But my question is slightly different. I'm going to ask myself, how do I formulate some of the theories that I've been interested in from the physics of the standard model so that I can put it on a quantum computer? First, I need to be able to write my quantum field in terms of qubits. Remember, qubit is a sort of a two-dimensional Hilbert space. And so I need to put my local Hilbert spaces and formulate it in terms of qubits. So this is what we call qubit regularization, right? We regularize our infinite dimensional Hilbert spaces maybe through some finite qubits, right? Because at the end, if a single site, remember, needed an infinite dimensional Hilbert space, like in a bosonic case, I'm done, right? And I can't do much. I have to really think about the even bosonic fields in terms of finite dimensional Hilbert space. It's actually a two-step process. Is something Wilson taught us already, right? We start with our desired quantum field theory. We regularize it using qubits on a lattice, so that the local Hilbert space here was infinite dimensional, whereas here the local dimension is just a finite dimensional Hilbert, right? We write down a model here, and then we have to go back and ask, how do we take the continuum limit and get back this field? That's our goal. We start with something here with infinite dimensional Hilbert space at a very local site, make the lattice model, and then figure out how to come back. So that's always a two-step process. From a renormalization group perspective, all this means is We had a traditional lattice model where I tuned myself here. Now I'm exploring another regularized model. This is called the qubit regularized model, which then produces the same physics. So from a universality point of view, this is maybe possible. I shouldn't say this is possible. This may be possible. And these are the kind of questions we can ask. So the interesting question here is, what is the minimal number of qubits I will need on each lattice site to be able to match this infinite dimensional Hilbert space to begin with? Does that even work? Or one, of course, way is to put it in some Hilbert space and then slowly increase it, right? That is a more conventional, simpler approach that most people are taking. They're saying, hey, don't worry about all these complications. Just start. I know the original model in the infinite dimensional Hilbert space works. So put it in some truncation and then slowly take it away. Make it bigger and bigger and bigger. At some point, you'll come back to the original. That is definitely true, right? But can we ask, what is the minimal number of qubits? So one of the things that I would like to do is, one of the main questions in the standard model is what is called asymptotically free theory. And what does that mean? This is actually a holy grail for particle physics, I would say, right? The standard model is built from this notion of asymptotic freedom. What it means is, at very short distances, things are all free. So I can write down my microscopic model very easily. But then as I go to long distances, all the interesting physics of interactions takes over and I reproduce my physics. Right? Such QFTs have no free parameters, but it can produce very rich physics. Right? And so in fact, these three people got the Nobel Prize in 2004 for discovering this feature in the standard model. And there's a lot of interesting data that has been developed so far to see how a dimensionless coupling can depend on a scale. And this curve is something that is universal. It can be understood. So of course, gauge theories are very hard to do. So we asked ourselves, can we reproduce this physics in a simpler setting, right? So just to see if the proof of concept works. Right? So what we did was we took a simple theory in two dimensions, one space and one time dimension. And this is something that physicists do all the time. If I can't solve the real problem, if I can't know what a cow is, let's make the approximation the cow is a spherical cow. Right? It's always something that's helpful. So it's like that, right? But it has a very interesting physics of asymptotic freedom. So you write down your model, right? There is a parameter G like you would like in the real theory. It's one of the nice features that it's exactly solvable. So the quantum field theory is completely determined and understood, right? Let me maybe, because of the time, let me go on. So one of the interesting outputs, because I have to tell you what exactly did we do to compare, right? One of the things that we call is the step scaling function. You take this theory, right? There are no free parameters, but I can put it in a box, right? The box has some length, let's say 1 meter. That then naturally induces a length scale in the theory, which we call a correlation length. That depends on the box size, right? And so this coupling G I told you is actually this ratio. And so I can then do an exact calculation and tell you how this, notice this is a dimensionless ratio of one length scale by another length scale. That depends on another dimensionless ratio, which is basically how that length scale would have changed if I make the box 2 times larger. This is related to Wilson's renormalization group. It's like a mathematical thing that you can actually do and compute it exactly for this model. So that black curve was known for that model. That comes from a continuum field theory calculation, right? The goal was to reproduce this black curve using our qubit regularized model. So what did we do? First step, remember, I have to take my continuum theory and regularize it on a lattice. So that we took, our continuum theory was a model on a surface particles were on the surface of a sphere at every site, right? That was the quantum mechanics. That we know from quantum mechanics can be written in terms of YLMs, right? but I have to keep all the y LMs. I can't just throw away some LMs. But he said, let's keep only the lowest one, L equals 0 and L equals 1. That is a 4-dimensional Hilbert space at each side. So that can be encoded in 2 qubits. So the continuum field was encoded by just 2 qubits at every side. Then we said, what is the model? Oops, I lost something. Okay. So to get asymptotic freedom, I need to show that there is, of course, the lattice scale where everything is not something that I want. There is some physics of some small box. Remember, I told you in the continuum, there must be a box. And then there is the large box. So this is where the physical limit comes. So this is non-universal. And these are the place where the continuum physics should emerge. Right? The qubit model should be able to reproduce that in that region. So in the step 2, what we did was we had to find a model that will reproduce the physics. And remember, at each site, remember it was a one space and one time. The time comes through time evolution. This is just space. At every site, there are 2 qubits. And the model is, we had to search. It was not obvious what that model was. We searched for the model and we found a coupling. And if we set that coupling to infinite, we seem to be able to reproduce the physics. And here is the results, right? So this was the dark line was our original model, original theory that we had to reproduce. And these data, if you hope, if you are with me, you'll realize that we studied on different lattice sizes, right? And so for j equals 3, remember the real physics only emerges at j equals infinity. But at j equals 3, you are off the axis, off the line, but then you come and start flowing on the line. Right? At j equals 5, you start off the axis, but then you go farther out here, right? And then you start flowing on the line. For j equals 10, you can go even more farther out, and then it starts flowing on the line. Of course, you might say, I haven't gone to, why don't I show this all the way down? If I do this calculation, if I want to come here on this j equals 10, I will need a billion lattice sites. Right? It's just the way, remember I told you how the lattice spaces is becoming smaller and smaller, the same length being reproduced. So I will need larger and larger lattice sites, but this is like a proof of concept that's actually working. Right? So with that, you might ask, is there a systematic way to extend all of these to other theories? Indeed, this is something that we did long ago, as I told you, as a postdoc at MIT. So in principle, you can formulate these theories, right? And you know that by systematically making the Hilbert space bigger and bigger on each side, you will be able to reproduce the real physics. But then the challenge, and this is also true for gauge theories, but the challenge is that what is the minimal number of qubits I need to be able to reproduce that physics? And that's sort of an interesting goal. And that's what leads me to the final thing, that can we start building this to build our universe with qubits. That, let me summarize. I hope you all are convinced that the universe is made out of particles that come from a quantum field. That's what we understand things. Quantum field theories in the continuum are hard to solve, right? So especially in the strongly interacting sector. Perhaps quantum computers can help, but we first need to build those theories out of qubits. Of course, there are systematic approaches to do that, but I think at the end, the goal may be to find a minimal model that's exciting, right? And be able to reproduce the physics that we need. So maybe our universe is one such minimal qubit model. Thank you.